Okay. I want to show you a couple things on the computer. We're going to use the big screen today, and I'm going to start with this problem. So here is this problem, which is a turntable, and it has a slot in it, and a mass slides in the slot. And this is exactly the same problem. It's an identical problem mechanically to the problem I've been doing with this bullet and this slot. This little weight slides inside the slot, and I shoot it across the room, and we make the joke about hitting a student and stuff like that. This shoots across the room, and this turns. Now, if this is sliding in here and it's frictionless, and this is turning on a hinge, then as this slides, this rod pushes on this bullet, which makes it go faster and faster, but it slows down this rod. Now, in the version of the problem I did before, we had a motor here turning this at constant speed. Now we do the version where there's a hinge here, so this one slows down while this one speeds up. And we'd like to know, how does this slow down as it speeds up? So this is a machine with various parts moving around various ways. Okay, this is the example I started. And problems like this get harder and harder. And if you're just at the point where you can start putting together problems like this. So one is I want to talk about this problem. If there's time, I want to go to talk about the double pendulum, and then I want to motivate this with a video, which I'll show you. I didn't show you the Laurie Anderson video this class yet, right? The Laurie Anderson video. I didn't think I did. Okay, so here's this problem, and now I want to set this up with giving you some context for laptop send-to-center display for what this looks like in terms of how you solve problems in general. Did you do it, or someone had to help you figure it out?
I figured it out.
Perfect.
It was right near the door, and it's heavy.
And it's heavy, sorry. I can have the keys, thanks. Get those screen lights off. Okay, so there's this book, which you might love or hate, which I am married to. And if you go to the end of that book, it has some various tables. And at this point in the course, I recommend, here's the last page in the book, which I want to talk about now. But at this point in the course, you could look through these tables, and they talk about moments of inertia and things like that. Here's a table which you could look at, which tells you different ways of thinking about position, velocity, acceleration. So position is position, velocity is velocity, acceleration is acceleration, but there are various ways you can calculate those vectors. Everything in this column is equal to everything else. Everything in this column is equal to everything else, but these are different ways to think about it. And this is just a summary of these formulas. Now, you could think, oh, I want to memorize these formulas, but again, like I said, do you know your middle name? Yes, you all know your middle name. Did you memorize it? No, you know it. And you should be getting to a point where you know these things, which means you haven't memorized them, but you have some feel for all the terms, and you just remember them. Anyway, we've now covered all of these formulas, and so you can have a look at this to just check your memory. This is a table in the back of the book. Here's something we haven't talked about much, but you could look at this, a different way to think about acceleration. Then here's another table, which we use various parts of various times. So always in this class, as opposed to statics, we're talking about linear momentum or angular momentum or kinetic energy. This is the right-hand sides of the equations that you have 0 on the left-hand side in a statics class. And they're different systems that you look at. So in general, you can think of what are these things, the linear momentum or its rate of change, angular momentum or its rate of change, or the kinetic energy. What is it for one particle? This row 2 here is basically what you did mostly in physics 12. What is it for a system of particles? You add up for the separate particles. What is it for a continuum? You add up for the separate particles, but you think of the particle formula as being a Riemann sum to define an integral over little bits of mass dm. And what is it for a system of systems? If you figure it out for one system and another system, you just add up. All these quantities are linear in that the linear momentum of a system, or its rate of change, or angular momentum, or its rate of change, or kinetic energy, or its rate of change, are all sums of those same quantities over the parts of the system, even if each of the parts is itself a complicated thing. Then there are special systems. In this class, the main system of interest is system number 2 here, in this, which is called 7, because 7 is 2 plus 5. System number 2 in this table is called equation 7. One rigid object in the plane. How do you think about its linear momentum, angular momentum, and kinetic energy? So these are the main formulas you deal with, combined with this system formula where you add things up. And then there's special cases if you're rotating about a hinge and so on. Okay, the main point, again, that I want to emphasize is that you should look at these tables at the back. Here's another table, which is about different ways that parts of systems are connected to each other. And when these parts are connected to each other, you get, for example, if we look at a system made of an L, 2 parts of an L, and we cut it here, what happens at that cut? Well, in that case, it's a cut of a rigid connection, and there's a force in a moment because both rotations and translations are prevented. How many degrees of freedom at that cut? 0. How many restrictions are there? 6 in 3 dimensions, or 3 in 2 dimensions, translation and rotation. And this table goes through all the different kinds of connections. Again, what am I trying to say is at this point in the course, you should go to the back of the book. You've been to this part of the back of the book, but you want to go to this part of the back of the book and learn, not learn all these things. Make sure you know all these things. If you know everything in these last tables, then probably you know everything you need for this course. What I wanted to talk about now is this very last page, which is a summary of how do you do problems in mechanics, in particular in statics and dynamics. So what this is a big flow chart for how do you do problems. What are you trying to do? You're trying to figure out something about the forces and motions of some system. So what are the stages in this? As you start out, so I'm just going to spend a few minutes on this table. You start out with basic modeling. You look at the system and just understand what is it? What things are rigid? In this class, everything is rigid except for springs. In 2020, you had to worry about which things stretched like rods and twisted like shafts or bent like beams. Which things can move and which things can't? How can they move? How are things connected? So you have to understand what the system is. Then there are various things that you can deal with. And these are the 2 sides of the equation F equals ma. So over here, we have the F side, and over here we have the A side. So to start out with, if you want to just look at the force aspects of things without worrying about the motion, which is all you do in statics, you start over here. If we want to understand the motion without doing dynamics, just geometry, you start over here. And eventually you're going to say F equals ma. You're going to take this stuff and make it equal to this stuff. So what are these 2 different sides? First, let's do the static side of things, the force side of things, the part of dynamics which is the same as statics, which is force modeling. What are the contact forces? What are the friction forces, which are a kind of contact forces? What are the forces at hinges? What about gravity, springs, and so on? All the different ways that the external world acts on the system or on subsystems. Because even though you're interested in this whole machine, say over here, in order to analyze it, you're going to break it into pieces and look at the forces of the different parts on each other. What's the big tool here is drawing free body diagrams. You draw it of the whole system, most likely, and of the components. If you draw free body diagrams of all the components, the information that you get from the free body diagram of the whole system is already there. Nonetheless, it's often useful to draw a free body diagram of the whole system. That's the force side of things. What about the kinematic side, which is not useful in 2020, but it is here? It's a description of the motion, and in particular of the constraints. one thing you have to do is you have to pick your basic configuration variables. So here's this picture of this system with this plate and this mass. We could have x and y coordinates of the mass, x and y coordinates of the center of the plate, or a bug that happens to be on the plate crawling around, and the rotation of the plate. But this system is not so complicated, so we pick simpler variables there, say the radius of the mass and the angle of the slot. Because if we know those two variables with the other constraints, we know the whole configuration of the system. Then what you want to do is you want to figure out from those variables and their derivatives, in this case is r and r dot and r double dot, and theta dot and theta double dot. If you know those quantities, then you can figure out the position, velocity, and acceleration of every atom, every bit, every mark, every point on every object in the system. And that's the kinematics analysis. The main feature in kinematics analysis is being able to find the motions, whatever you mean by motions, of all points in the system in terms of your basic configuration variables. So hinges and so on. You want to find any angles, rates, and accelerations. If you do this, then basically you're done with the kinematics. The force analysis you're not done with when you draw the free body diagrams. You have to write your basic equations of motion, or in statics, force and moment balance. What are they? You take the forces and moments that are in the free body diagrams. If they're not in the free body diagram, you can't use them. Then you take the velocities and accelerations and you write your basic balance equations. Linear momentum, angular momentum, or energy or power. What are these balance equations? Usually we're dealing with F equals ma. We call it linear momentum balance, but we really mean the forces equal the rate of change of linear momentum. Or angular momentum balance, which is that the sum of torques equals the rate of change of angular momentum. Or the statics equivalent, where you neglect the inertial terms. You assume the mass times the acceleration is negligible in statics. They're never zero, right? Everything's always moving. But in statics, you think those terms are small, so you say the forces add up to 0 and the moments add up to 0. Or you could do power balance or energy balance, that the work of all the forces on the system is the rate of change of its energy, assuming there's no heat flow into the system, or the rate of change of the rate of work, or the power on the system is the rate of change of energy. These are your basic equations. Now, these equations give us, in dynamics, what we call the equations of motion. How do we get the equations of motion? We take these balance equations and we want to find the motion. So there are various ways we can sort these equations out. The simplest way of sorting it out is if you're doing statics. You take the balance equations, force and moment balance. You take the configuration that you know the system is in, and you solve for the forces. That's where 202, 2020 is on this diagram. There's an equivalent dynamics problem, which we call instantaneous dynamics, where you know the configuration of the system at some instant in time, and you want to solve for some accelerations or some forces in terms of the others. It's a version of dynamics which is exactly equivalent to statics. You forget that the equations of dynamics are differential equations. You just think of acceleration as a quantity, and you want to find that quantity the same way you want to find force. That's the thinking that goes into D'Alembert mechanics, where you think of ma as a kind of a force, which is a confusing way to think, I think. But nonetheless, the ma terms are right in the list of equations, just like the force terms. And the I alpha terms are right in there like moments. And in a given configuration, you want to solve for variables of interest. Another sort of simple version of dynamics is called inverse dynamics. It's where you know the motion of the system, and all you want to know is the forces. In inverse dynamics, somebody has made a movie of the system, or somehow you know exactly how it's moving. Therefore, you know somehow what the positions, velocities, and accelerations are at every instant in time. Therefore, when you write F equals ma, or the angular momentum equation, the right-hand side, you know it. So you're just solving for the forces. It's just like a statics problem, where someone's given you some forces and you want to know other forces. Here, they've given you the motion, which is the ma terms, and you want to find the forces. This is called inverse dynamics. It should be called forward dynamics because it's a simple problem. It's called inverse dynamics because it's backwards of the usual problem, which is the harder one. Okay, now we get down to here. This is the whole hard part of dynamics. Well, what's the hard part of dynamics? Actually, the hardest part, technically, is this part here. It's the kinematics, figuring out velocities and accelerations in funny coordinates with funny information given. This part, traditionally, is the hard part because it involves solving differential equations. Nowadays, solving differential equations is easy. You plug it into MATLAB, and this is no longer the hard part. Okay, so now we're trying to find the motion of some system. The motion is unknown. What do? We want to write differential equations, and we want to solve them. So what does it mean to write differential equations? It means back up here, we've got some configuration variables, say r and theta, and we want, given the current configuration, that's r and theta and r dot and theta dot, we want to find what are r double dot and theta double dot. If we can figure out r double dot and theta double dot in terms of the current configuration and current velocity, those are called equations of motion. Those are differential equations we can solve in principle on the computer and with luck with pencil and paper. Now what do we need to do? We don't actually need to write a formula for theta double dot equals or r double dot equals. All we need is in our MATLAB right-hand side file, we need that the last line of that program tells us the rate of change of the variables. So all we need is a way to find, by sequence of computer commands, what is the acceleration or second derivative of r and what's the second derivative of theta, or the second derivatives of all the configuration variables. If you're lucky, you can solve these with pencil and paper. And then another kind of luck is if you go back up here, and rather than use rate of change of linear momentum, sometimes we can get a conservation law and just use literally linear momentum balance, which is that the linear momentum of the system is constant, or angular momentum of the system is constant, or energy of the system is constant. And that gives you a big shortcut for solving some special problems, like the problem, the napkin ring problem on the prelim last time. You could make lots of progress just by using conservation laws without having to actually writing the differential equations and solving them. Okay, now you plug that into your MATLAB program, or you're really good at Laplace transforms or solving differential equations with pencil and paper, and you get positions and velocities and accelerations and forces as a function of time, and you make plots and make animations, and you think about it and you say, oh, that means the thing falls down or doesn't fall down or breaks or doesn't break, and you're done with your dynamics. Okay, and this is all of statics and dynamics done on one page. Anybody want me to explain any part of this chart, or does anybody have any questions about any part of this chart? So as you are working on the homework problem or exam, you should be able to find yourself in this chart. This sort of map, this overall flow chart for solving problems. Somebody asked some question. Okay, just out of curiosity, how many of you have spent more than 30 seconds looking at this page already? Raise your hands. How many have not? Okay. I'd say this is, this is the kind of thing, when I think the best way to study, by the way, is not with books. It's not with reading the book. It's not watching the lecture videos. It's maybe not even doing homework problems. The most important part of studying is thinking about the material, with, like when you're walking around or in the shower or going to sleep or waking up. This is the kind of thing you might try to think through in your head to organize the material. Okay, so I'm going to stop this for a while. No questions? Mute. I failed. It says mute, yes. I pressed the mute button. Then I press center display. Program, mute. Center display. Mute. How about off? Okay, now we get to our first quiz question. No talking. Quiz. Can anybody not read the quiz question? Any questions about the question? Yes? That's part of the question. Degrees of freedom of what, did you say? Oh, of that system over there. I think you said degrees of freedom is what? Actually, I didn't even mean to say that. DOF is what? I don't want to mess with the screen anymore. I'll just tell you how the vote is going. Somebody stole our iClicker remote. Josh Tashman stole the iClicker remote. Okay, 5 seconds left to vote. Okay, vote is over. And 3 people voted A, 14 people voted B, 5 people voted D, and 3 people voted E, and 53 people voted C. And this being a democracy, we accept answer C as correct. Any questions about this question? Yes?
Just so I can visualize, the degrees of freedom are the bug. It can move in a circle with the turntable, and it can move in this little slot.
That's correct.
Okay.
But it's not a bug. It's a slip. This one is not crawling, right? You sprayed it with some wasp killer, and it's slippery. And it was actually turned out to be 3-in-1 oil, not wasp killer. And this slides in the slot. What? Calculate what? Okay, so this is something that I do not know how to calculate. This is something I have to look at and talk about. So in this case, I look at this system and I say, how many ways can this move? Well, this can rotate and this can slide. If I knew this angle and I knew this position, I would know where every atom is here. Therefore, I get the number 2. Yes?
Think of the system as the entire thing, like wouldn't it actually, like how would it not be one? It's like the bug's part of the system, so it's moving until it's outside of the cylinder too.
Because we do not have some relationship between these two. They're not constrained to move in some way relative to each other. So this can slide in here, and this can rotate.
They're not related?
What?
They're not related?
They're related by the differential equations, and in the end, there's just one trajectory of the whole system. But when we talk about degrees of freedom, we're not talking about the output of the equations of motion. We're talking about the geometric constraints. So before we get to the differential equations, so we're allowed to violate Newton's laws and Euler's laws, and we're allowed to put our fingers on the system and move it around. How many different numbers are there to describe the system before we get to the differential equations? After we get to the differential equations, all systems have 0 degrees of freedom. They just do what the laws of mechanics tell them to. Does that address your question? It's a very good question, as are all of the questions that all of you ask. Including those two guys. Where are they?
They're writing the program.
Okay, so how do we do this? I'm going to repeat what I did last class on this example. Is we draw free body diagrams, and there are 3 free body diagrams we can draw of this system. One is we can draw a free body diagram of the whole system, in which case we've got to show that which is holding it in place. So I can call this ROX, ROY, I guess, and ROX. Somewhere on the side, I'll put something to show that I've got some coordinate system, so I can use that if I want to. I can draw a free body diagram of just the turntable, and I can draw a free body diagram of just the mass. In this case, there's some force N, and we've got good 3-in-1 oil on this dead wasp. And here we've got, you push the wasp around, it doesn't sting you, but it pushes back anyway. And this free body diagram has to have on it the same force. And somebody asked, can I use this force both times? And the answer is yes. This force is the same as this force. It's not a double counting, because this is not, say, some part of a truss where 2 bars intersect a joint. You have to decide which force the bar acts on. Or you might have to decide that. And if somebody cares about it on the side, but careful to make it clear that it's not a force, I can show geometry information. By this point in the course, I think most of you should have learned that what I've said at the beginning is that if you get the free body diagram right, and you can do vector algebra well, chances are you can do homework and exam problems on your own. Okay, now we've got these free body diagrams. What equations of motion can we use? What linear momentum balance, angular momentum balance, energy equations can we use? Well, we can use all of them. And we could write down for each of these free body diagrams an infinite number of those different equations. Why is that? Because linear momentum balance, well, linear momentum balance is just one equation. But angular momentum balance, we get to pick whatever reference point we want, and we could pick any reference point we want. Power balance, one equation. Energy balance, one equation. We could try to write conservation of angular momentum, conservation of linear momentum, lots and lots of choices. So at this point, you can just write down lots of equations, so you can try to figure out what you're trying to get at. Let's say we're just trying to figure out how this thing moves. For example, I have a puzzle problem for you. If I start this thing rotating, this thing's going to go faster and faster. This thing's going to go slower and slower. As time goes to infinity, does the angle that this rotates go to infinity, or does it go to some finite number? It's a puzzle problem, right? Let's say we want to know the answer to that puzzle problem. Okay, probably nobody has, with confidence, an answer to that question. But here it is, a simple system, a simple question, and you have to use math to figure it out, probably. Anybody feel confident of an answer to that question?
Can you repeat the question? I have a question about the question.
The question is, I launch this thing at some angular velocity, and maybe this has some initial velocity, and this slot is infinitely long, but this moment of inertia is not infinite. So it's a very mathematical kind of question. Does the angle go to infinity or not? Now, if the slot was finite in length, obviously the angle goes to infinity because there is some angular velocity when the mass runs out. And then if we have a perfect hinge at 0, which is our assumption, then the angular velocity is constant because the angular momentum is constant because there's no torque on that system. And therefore, the angle increases linearly in time. That goes to infinity. But the question is, if the mass is still in the slot, then the mass is being perpetually accelerated by the disk. The disk is being perpetually slowed by the mass. Certainly, the angular velocity goes to 0 as time goes to infinity. But does the integral of the angular velocity go to 0 or infinity? Does it go like 1 over t squared, which is a bounded integral, or does it go like 1 over t, where the integral is unbounded? So probably you don't have an answer to that question, right? Anybody want to venture an answer? Yes?
Well, since it's doing work on the particle, is there a fixed amount of distance that it would have to, that it can rotate before it runs out of energy?
No, that reasoning doesn't give you an answer because the power is always bigger than 0, but tends to 0. And so the question is, does it tend to 0 as 1 over t, or as 1 over t squared? 1 over t or something bigger than that, but still goes to 0, or 1 over t squared or something smaller that still goes to 0. Right? So you can't tell from that. How about, is there a special case where you could tell the answer and maybe just guess that the general answer is like the special case? Can anybody think of a special case where they can figure out the answer? Yes?
If the bullet starts in the middle of the...
If the bullet starts in the middle, then what are you going to say?
It's going to go to infinity.
What goes to infinity?
The angle as time.
If the bullet starts in the middle and starts with 0 radial velocity, it just sits there and the disk keeps spinning round and round. Okay, now that's a special case, but it doesn't help us very much, right? Another special case that maybe would be helpful. Okay, well, I've got one. What if yeah, you got one?
The bullet starts at infinity.
If the bullet starts at infinity. Now, I use the word infinity, and it doesn't sound crazy and abstract. You use the word infinity, it sounds crazy and abstract to me. Now, I hope it's not a symmetrical situation. I don't know about that one. I'll have to ponder that. Okay, well, here's one. What if the disk has 0 inertia? Then the disk just floats around and goes for the ride, and the bullet does what it would do. What's the path of the bullet then? It's a what?
A shell.
A shell. Now, bullets are called shells. A spiral, that kind of shell. Well, if this disk has no inertia, then when we write the angular momentum balance equation about this point, it has to be that n is equal to 0. If we have the torques about this point, it's the rate of change of angular momentum. The rate of change of angular momentum is 0, so this n has to be 0. Which means this n has to be 0, which means the bullet has no forces on it, which means its path is a straight line at constant velocity. So if this is launched, and this thing has no inertia, it just goes for the ride. It's like tracking the thing. It's like looking at the bullet and just following along, and the bullet just goes in some straight line at constant speed. And this slot just goes to a finite angle, which is parallel to the line that the bullet's going on. Is that clear? Who understood what I just said? Who did not understand? Do you want to ask a question about that? Okay, let me just try to help your thinking. If the inertia of that disk is 0, it's just a distraction. It does nothing. It just moves along and watches. So the bullet does what it would do as if the disk was not there. How can you prove that? Is because if the inertia is 0, angular momentum balance about this point says that the torque is the rate of change of angular momentum. But if the inertia is 0, the rate of change of angular momentum is 0. So this torque has to be 0. So n has to be 0. n has to be 0. The bullet goes in a straight line at constant velocity. If the bullet goes in a straight line at constant velocity, then at the end of time, after the sun is burned out, this thing is parallel, almost parallel to this line. It only goes a finite angle. Now you could say, how can it rotate if there's no force? This is what all of statics is about. So all of your statics analysis is about things which are moving all over the place. And you assume that the sum of forces on them was 0. So when you say there's no force, how does it move? It's because it has no mass. Now you could say, which is more true? Is the force more 0 or is the mass more 0? If you really think the force is more 0 than the mass, then it doesn't move. If you think the mass is more 0 than the force, then it's got infinite acceleration. What you're saying is that the mass and forces are both so small that the force is balanced and the motion is undetermined. Yet in this problem it is determined because there's a slot there. Does that address your question? But that question is one you should stop and suffer over, right? That's just the kind of thing you'll be stuck on again and again. Okay, more questions? Yes?
So we have a massless bead moving in the slot of an inertialess plate.
A massless bead? No. If I had a massless bead moving in an inertialess plate, then everything would be undetermined. So I assume, so in this special case, let's go back 5 minutes. I gave you this puzzle problem with the real plate and the real bead, real with all the idealizations. Does the plate go an infinite amount or a finite amount as time goes to infinity? Then I said, is there a special case we can work out? Let's work out the special case where the inertia of the plate is 0, but the mass is still not 0. In that case, we have that this n is 0, the bullet goes in a straight line at constant speed, and therefore the slot rotates a finite amount. If I said the mass of the bullet was also 0, then I have a problem that's completely undetermined. I can't say anything about it. It's a non-problem. I have no forces, I have no masses, I have no laws of mechanics. It does who knows what. Does that address your question? Yes?
With that trajectory you drew there, is that the way that the velocity was pointing? Or was the velocity along the...
I drew it, this dotted line, assuming that I had some initial radial velocity and some initial angular velocity, and the net velocity of the bullet at time equals 0 was in this direction, and therefore the bullet is stuck. Despite all the distraction of polar coordinates, the bullet is stuck going in a straight line at constant velocity.
So eventually it would have no angular velocity?
So eventually, theta dot is going to go to 0 no matter what for all problems and all inertias. And in this case, if you follow this along, watch my finger. As I point at this bullet, you will see that my angular velocity of my finger goes to 0. It's a funny thing about these polar coordinates. If we take the equation F equals ma and write it in polar coordinates, we have mass r double dot minus r theta dot squared er plus r theta double dot plus 2 r dot theta dot e theta. This is F equals ma in polar coordinates for any particle, this particle or any other one. If I do the special case where this is equal to 0, there's no applied forces, then I get something over here. And if I take the dot product of both sides with er and e theta, I get that r double dot minus r theta dot squared is equal to 0, and I get r theta double dot plus 2 r dot theta dot is equal to 0. This is, we could write this then as r double dot is equal to minus r theta dot squared, and theta double dot is equal to 2 r dot theta dot over r. This is two nonlinear differential equations. Trying to solve these is a mess. Interpret the solution. The solution of this is that r as a vector is equal to R0 plus V0t. How do you get from here to here? If you're very algebraically and calculus-wise inclined, you'll do lots of work. So these polar coordinate equations, even though they help us do some problems, if we take the very simplest dynamics problem, which is a particle with no force on it, and try to find the motion, it gives us a mess. Some problems, it makes it easier. Here, the simplest problem, it gives us a mess. To get from here to here, I don't even know if I can do it. I would start here and try and interpret that. Okay. Aside. So polar coordinates, as much as they can help, they don't help you with every problem. Okay, so now we want to figure out equations of motion for this thing. How do we figure it out? One way we can do is we can start with this free body diagram, and we can write angular momentum balance with respect to 0 for this thing. So what does that say? It says that the sum of moments on this system is equal to the rate of change of angular momentum with respect to O. Now for this system, what's the rate of change of angular momentum with respect to O? What's the sum of moments? For those of you who weren't paying attention, blah, 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 blah. Okay, thank you. And then how do we figure out the right-hand side? Well, this is a system of systems. So we look at the rate of change of angular momentum of this, add it to the rate of change of angular momentum of this, and that gives us the right-hand side. The rate of change of angular momentum of the system is the sum over all the atoms. We can break the atoms into clusters, in this case one rigid object and one particle, and see what we get. So for the rigid object, we get I0 theta double dot k. And then we add to that the rate of change of angular momentum of this thing spinning around. What is that? That's the position of that thing crossed with the acceleration of that thing multiplied by the mass of that thing. What is the acceleration of that thing? Well, we could use polar coordinates. It's exactly this. What's the position of that thing? So we have this polar coordinate formula. What's the position of that thing is r e sub r. So we're going to take the cross product of r e sub r with this thing over here. So we just get out this collection of terms here. So we get the 0 is equal to I0 theta double dot k plus this cross product of r sub er, with this collection of terms here. So we have r times the mass times all this stuff. So we have plus r times the mass times r theta double dot plus 2r dot theta dot, and this is all in the k direction, and then we can put this all together and we can say theta double dot is equal to, and then we solve for what's left over. There's a I0 plus mr squared on the bottom, and on the top there's a minus 2r dot theta dot m. So that's one differential equation, which is not enough. We need an r differential equation also. But it's enough to figure out pretty much, like how the disk slows down. How do we figure out the other differential equation about how r changes in time? It seems like we should use F equals ma for the mass. So we use linear momentum balance for the mass. What does that say? It says the sum of forces acting on the mass is equal to mass times the acceleration. We have an n e theta acting on the mass, and that's the mass times the acceleration. The acceleration is now, I'll just copy that formula again, is an r double dot minus r theta dot squared e sub r plus r theta double dot plus 2 r dot theta dot e sub theta. And we don't really care about this theta stuff anymore. So we take this equation, because we've already got that pretty much figured out. We take this equation, take the dot product of both sides with e sub r. Sorry, with e sub r. And it tells us that r double dot is equal to r theta dot squared, just like we had before for the case where the gun was controlling things. Okay, so these two equations then are our equations of motion. I'll call this 1 and 2. 1 and 2 are the equations of motion. Okay, any questions about how I got those equations? Now, if I want to know how this thing actually moves, I have to solve these differential equations. These now are nonlinear differential equations. Can you solve with pencil and paper? Yeah? I'm missing an r where?
1. Equation of motion 1.
In the numerator, I have a r up here. Thank you. Can you solve these differential equations with pencil and paper?
Yes.
You can?
No, not personally.
Who can? I gave this as a puzzle problem to this class once, and I was sure that nobody could, but I was wrong. One of the TAs figured out it's you can write the solution in terms of a Bessel function of the second kind. Okay, good luck to you. Yeah. Okay.